Hi everyone, it is Mr. Youngren once again, and today we're going to continue working with logs. We're going to actually move away from the graphs now. We're going to start talking about something called log rules or log properties, which is going to start on page 190. So let's go ahead and get there now. So once again, this is page 190. And before we start talking about these log properties, as always, you do have an opener. This opener is aimed to kind of give you an idea as to how do we deal with different kind of exponents. And when we're dividing terms that have the same base, what do we do with their exponents? We have an exponent raised to another exponent. What are all these rules? Because they're going to come into play here. There are things that you might have known before, but either way, why don't you see what you come up with? So go ahead and hit pause, work through these. It is important that you try, even if you don't have an idea. And then you can hit unpause to see what you should have gotten. So go ahead and pause right now, and then unpause once you're ready to see what they should have been. All right, well, here's what you should have gotten. I'm going to kind of give a quick overview of how I come up with these. So that way we're able to do these things as we're working with logs, because a lot of exponents show up with logs, which makes sense because they're inverses. But here's kind of the general gist. So how did I come up with 12? I came up with 12 by adding 4, 6, and 2. So all the bases of x, I want to add their exponents when they're multiplying. Now, why do we do that? We do that, and here's how, because I forget this sometimes. Maybe not now that I've taught math for a certain amount of time, but you're going to forget it. So I'm like, okay, well, what's something easy and what I know? Well, x squared times x cubed. If I think about what's really happening here, x squared is really x times x. And then x cubed is x times x times x. And so when I look at how many x's are being multiplied, there'd be 5 there, which would give me x to the power of 5. And so if I look at how I go from 2 and 3 to get 5, I have to add the exponents. So multiplying same base, add the exponents. And that's how I came up with 16 as well, right? 7 plus 9 to give me 16. So multiplying same bases, add their exponents. The next one, if I have an exponent raised to another exponent, we're actually multiplying. So 4 times 7 gives me 28. 6 times 7 gives me 42. Now, once again, why is that the case? Well, let's think about if I had x squared to the power of 3. What does that mean? Well, anything raised to a power means the base times itself that many times. This is really x squared times x squared times x squared, right? That's what x squared cubed would mean, because we want to multiply x squared by itself 3 times. And then when we break down what x squared is, it's x times x, and we have that 3 times. So x times x times x times x times x times x. How many total x's do we see? That would be 6. So x to the 6th. So raise an exponent raised to another exponent, we want to multiply. And then the last one, if we're dividing exponents, so x to the 5th divided by x cubed, we're actually subtracting them. And so this would be x to the 5th or x to the power of 5 minus 3, which gives me x squared. The one that might be kind of confusing here is, why does y to the 10th over y 15th give us y to the 5 on bottom? There's 2 ways we can approach this, so I'm going to explain both of them. If I subtract these, that's really y to the 10 power of 10 minus 15, which is y to the power of negative 5. If I have a negative exponent, that changes the location of that base. So we can say everything is a fraction by putting it over 1. And so essentially when I have a negative exponent, I want to flip that. And so this base goes to the bottom and the 1 will come up top. So this is really 1 over y to the power of 5. And that's why I got that there. Now, another way to think about this is if I have, let's just say, let's not have too many y's here. So y squared over y cubed. This is really y times y divided by y times y times y. And in your last unit of rational functions, we know that anytime we have a bunch of terms being multiplied, if they're the same on top and on bottom, they divide out. So those y's divide out. Those y's divide out. And all I'm left with is 1y on the bottom. And so in this case, I would have had 10 up top, canceling with 10 on bottom, leaving me with 5 left over on the bottom. So if you don't remember the rules, kind of break down what their definitions are, just like what I'm showing you here. I know it looks kind of complicating, but it actually is a pretty basic approach to remember all those exponent rules. All right, well, that's our opener and kind of unrelated to logs, but like I said, we're going to need them. So when we're working with logs, logs have a lot of different rules and a lot of properties of how we can go from either one log and break them up into more than one log, or we might even do the opposite. And if we have multiple logs, how do we condense them? And we're going to have lessons on both of these. So we're going to take a couple of days to do these. Now, it's important that we remember these. So you might want to, I mentioned in the last video of maybe kind of keeping a record of the important notes from what you're seeing in this unit. You might want to take all the rules and put those on that note sheet, or maybe even create a note card. So what the heck's going on with all these? So our first rule, the name doesn't really matter. Product rule, quotient rule, doesn't matter. But basically what this is saying is if we're taking the log with the base b of two things that are being multiplied to each other, we're going to split them up to two different logs where we add the two logs together. So it becomes log base b of m plus log base b of n. So an explanation, or what I like to describe this as, is that multiplication is friends, or it leads to addition. Now, your teacher might have another way of explaining this, a more clear way. Maybe you have another way of explaining this if you got it from somewhere else. But basically, I'm like, okay, if I see the log of two things being multiplied, I can split them up into two different logs being added together. So there's that multiplication leading to addition. So it's log base 5. That's where the 5 came from. And plus log base 5 of 25. And this does have some practical value. So let's go ahead and look at what I mean by this. Now, anything that applies to logs also applies to ln, which is the natural log. We don't need to change this, but remember, natural log is a log with a base of e. So if I am wanting to go from natural log of 8 times x, I can split this up because I know that multiplication leads to addition of natural log of 8 plus the natural log of x. And that's it. So really a quick, easy thing for us to do. In fact, why don't we just do all these? So I have log base 4 of x times y. Its corresponding log would be log base 4 of x plus log base 4 of y. And then last one, we have log. There's no base. Remember, if there is no base there, I might fill it in with a 10. I like to do that just so that I always remember what that base is. It can be really helpful. Some of you may not need that, but this is log base 10 of 100 plus log base 10 of x plus log base 10 of y. And so we had 3 things being multiplied, so 3 separate logs. Now this has value. When we start solving equations with logs, we need to be able to move back and forth by using these properties. So really important that we can do these. And I would say that these are basic. We're going to get to some more complicating ones once you actually try practicing on your own. All right, next rule is the quotient rule. So the quotient rule, again, the name doesn't matter. Basically, this is saying if we are taking the log of 2 things that are being divided, we can split them up and subtract them. Now, order is really important here. When we talk about adding, order doesn't matter, right? 2 plus 3 is the same thing as 3 plus 2. Same thing with multiplication. 3 times 2 is the same thing as 2 times 3. But down here, with division and subtraction, order is important, right? 5 divided by 1 is very different than 1 divided by 5. And 5 minus 1 is very different than 1 minus 5. So the order is super important. So whatever is up top needs to be the first log that we write, and we're going to subtract it from the denominator. So it's always numerator minus denominator. That's really, really important that we recognize that. So again, my explanation is just simply that division leads to or is friends with division. Ignore my spelling. There's a reason why I'm a math teacher. Division leads to subtraction. So if we look at it, if I have a log base 5 of 125 divided by 5, yes, you might be like, well, can't you just do 125 divided by 5? Of course. But just to show you the property, I could take the numerator, log base 5 of 125, and subtract it from the log of the denominator. So log base 5 of 5. All right, let's practice a couple of these. And maybe what I'll do is I'll do the first one and then have you hit pause and do the next 2. So I need to take the numerator first, so log base 7 of 49, and subtract it from the denominator of log base 7 of z. And that's it. So why don't you go ahead and hit pause real quick, and then I will have the answers for the other 2 right after that. Okay, here is just the subtraction step where, again, we're taking the top, splitting them into two logs and dividing it by the bottom. Over here on number 6, the top of this fraction is 81x. So I actually have two things being multiplied there. So we can actually use multiple properties, and that's actually what I want you to do. Same thing with the bottom, right? That's y times z. So in this case, we can break apart or use these properties even further. So what I can do is I can say, okay, since I'm subtracting these, I can go ahead and take these multiplication, or 81 and x, which is being multiplied, and I can split it up to two logs that are being added. So this is really log base 9 of 81 plus log base 9 of x. Now, because I want those grouped together and because subtraction matters, I'm going to put some parentheses around this. So then when I split up the next ones and I subtract the addition, or the what's being multiplied y times z, that negative, if we were to distribute it out, would make sure that everything is getting subtracted correctly. So parentheses are really important when we're doing more than one property. So this is log base 9 of y plus log base 9 of z. And this is where they start to get complicating, right? Where we start using more than one log, or more than one property, excuse me, to start to either break them apart or even condense them. So if you're like, I'm still kind of confused, you're going to work through these with your corresponding teacher through class when you get there tomorrow. So be patient. If you don't understand it, practice makes perfect. We got lots of practice for you coming up on the independent practice. All right, last one is, again, the name doesn't matter, the power rule. Basically, all that's saying is if we are taking the log of something that has an exponent, the exponent can become the coefficient and vice versa. So I could also take this coefficient and make the exponent if need be. So again, my explanation is that the coefficient leads to or is friends with exponent. And so again, an example, if I have log base 5 of 25 to the power of 4, really that's 4 times the log of 5, or log base 5 of 25. So just taking this and moving it to become the coefficient, which is going to be really helpful once we start solving. So again, let's look at one. And then we'll let you try the last two. So natural log, once again, that's a log with the base e. Actually, why don't we do this time? Instead of natural log, why don't I write log base e of y to the 5th, and we'll work with that. It's the exact same. Okay? A natural log is a log with a base e. So here, all I needed to do is take this exponent and make the coefficient. So this is really 5 times the log base e of y. If we left it as natural log, it would be 5 natural log of y, where I don't need to write the base. So I like having the base. If you don't want the base, leave it as natural log, doesn't matter. All right, why don't you go ahead and hit pause, work through 8 and 9, and then that'll conclude this video. Okay, so here's just the property on its own where I'm taking that exponent and putting it in front. But some of you might be looking ahead and saying, well, I did that, but I see that I'm still multiplying. Could I break this up even further? And the answer is absolutely. When I do that and we have this coefficient, that coefficient needs to follow with every new log that we write. So if I were to take this even further, y z is y times z. So this is an example where multiplication is going to lead to addition. So 3 log of y, remember that's base 10, would be the same as 3 log of z. Now, another way I could have gone about doing this is using my exponent properties. One thing I talked about in the opener is if I have an exponent raised to an exponent, and some of you might be like, well, y doesn't have an exponent and neither does z. I would say, yes, they do. Their exponents are 1. And so I can multiply or essentially distribute this exponent to the other exponents and multiply them. So this is really log of y cubed times log of z cubed, which now I can go ahead and use that multiplication leading to addition property. And then the last thing would now be to take that exponent and put it as a coefficient, giving us the exact same log as what I had above. Just another approach of how we can get there. And there isn't one that's better than the other. Okay, I just want to show you that there's multiple ways to kind of figure this out. All right, last one. Once again, I brought the 5 over. I'd see that I'm multiplying 64 in z. So I'm going to just rewrite this as 5 log base 4 of 64 plus log base, oops, I forgot the 5. That 5 needs to come with 5 log base 4 of z. And we're all done. All right. Well, once again, thanks for watching. Make sure you complete your video check-in and have a great rest of your day.